Hello, everyone. My name is Rajesh Jayaram, and in this talk, I'm going to tell you about testing positive semi-definiteness via random submatrices. So this is a joint work with Ainesh Bakshi, also from CMU, and Nadiia Chepurko from MIT. Okay, so let's begin with the definition of a PSD matrix. So a matrix, an n by n matrix A, real valued, is said to be positive semi-definite if it is symmetric and if all of its eigenvalues are non-negative. So specifically, given an n by n real symmetric matrix, all of its eigenvalues are also real. So we can order its eigenvalues, lambda 1 of A, lambda 2 of A, so on down to lambda n of A. And A being PSD is equivalent to all of its eigenvalues being non-negative. Okay, so that was the definition. So I'll begin with a very simple fact, which will be useful for the remainder of the talk. And it'll be a good fact to keep in mind. And this simple fact just says that if A is a PSD matrix, all of its principal submatrices are also PSD. So a principal submatrix is just a submatrix, which we denote A sub T, which is induced by selecting a subset T of the n indices and looking at the square submatrix whose rows and columns are in the set T. So it's just a square submatrix induced by a single set, and this is a principal submatrix. So if A is PSD, all of such principal submatrices are also PSD. Okay, another interesting fact to note is that if we wanted to, in general, test whether a matrix was PSD, we'd have to compute an eigen decomposition to look at the eigenvalues. And in practice, this takes n cubed time, or in theory, this takes roughly n to the 2.373 time with fast matrix multiplication. It's the current exponent. Okay, so why would we want to test whether a given matrix is PSD? Well, it turns out that this is a rather ubiquitous problem in computer science, and it shows up in a number of places. For example, testing whether a function, which is twice differentiable, is convex, locally convex at a point. Well, this is just the same as testing whether the Hessian is PSD. Similarly, testing whether a finite metric is embeddable into Euclidean space. It's known that this also reduces to testing whether a given matrix is PSD. Another important application is testing the feasibility of a semi-definite program, which has a constraint that the get input point needs to be a PSD matrix. And there's a number of other applications as well where you would want to test whether a given matrix is PSD. Okay, but those will be discussed further in the paper. So I'm now going to mention a very simple algorithm, which will be the main algorithm and the only algorithm which we actually use in this talk, although it need not be the only algorithm that one uses for testing positive semi-definiteness. And it comes out of this very simple fact. We know that if A is PSD, all of its principal submatrices are also PSD. So here's a very simple algorithm. We're just going to sample a bunch of random principal submatrices, AT1, AT2, up to ATK. And we'll look at the entries in those submatrices, and we'll compute whether or not those submatrices are PSD. And if all of them are PSD, we'll say PSD. But if any one of them fails to be PSD, then we immediately return that the overall matrix is not PSD. Now, we know that this algorithm, while very simple, has a very nice property, which is called one-sided error. The reason this algorithm has one-sided error is because of this very simple fact up here. In particular, what this says is that if A was a PSD matrix originally, the algorithm will always output PSD. It will never erroneously say not PSD when the original matrix was PSD, because all principal submatrices of PSD matrix are also PSD. This algorithm is also very efficient insofar as hopefully the submatrices are small. So the runtime is only the runtime required to compute an eigen decomposition of a much smaller submatrix as opposed to the whole matrix. So the principal goal of this talk is to discuss when does this algorithm work, and when it works, what is the optimal query complexity of it? How big do these submatrices we sample need to be? So the question is, can the positive semi-definiteness of a matrix A be tested by testing the positive semi-definiteness of random submatrices of A? This is the principal goal of this work. And we'll work in something which is known as the bounded entry model. So this just says that the entries of A are required to be bounded in magnitude. All the entries are between -1 and 1. And we'll note that in some sense, one could always scale down the matrix by a large enough factor to satisfy this condition. So it may seem like this is without loss of generality. On the other hand, as we'll see on the next slide, by doing this scaling, we would affect the distance to the PSD cone. So it's not entirely without loss of generality. But one can see that naturally, if we wanted to test spectral properties such as positive semi-definite matrices while making only few queries to the entries of the matrix, it's important that we have some limitation so that some very, very large entry can't be hidden somewhere in the matrix, requiring us to read the entire matrix. So this model, a simple model, was called the bounded entry model by Balkin, Lee, Woodruff, and Zhang, who studied it to test spectral properties of matrices, such as the spectral norm and the Schatten norm. And this work, again, we are testing spectral properties of matrices, whether a matrix is PSD. And there's also a slightly less general model called the bounded row model, where rows need to be bounded in norm by 1, which was considered earlier to test spectral properties. Now, I'll mention that while we can always scale down a matrix to satisfy this, this bounded entry, there are several examples such as graphs or bounded multigraphs, the adjacency matrices of these, also correlation matrices and recommendation systems, which to begin with are already naturally bounded. So in these cases, there would be no loss for considering this model. So here's the problem that we have at hand. And we consider this from the so-called property testing framework. So given a symmetric matrix A, an n by n symmetric matrix with bounded entries, our task is to distinguish with constant probability between the case that either A is a PSD matrix or A is epsilon far under some metric from the PSD cone. So here this epsilon far means the distance under some metric from A to the PSD cone is some function of epsilon. It's parameterized by epsilon. And we want to distinguish these two cases, making as few queries as possible to the entries of A. And we want to make fewer queries as epsilon becomes larger. Okay, so, and one note that I'll quickly make is that here I included the property that A was symmetric. And actually in the paper, you'll see that there's relatively simple arguments that shows that the things that I'm about to tell you about will always hold even if the matrix is not symmetric. There's relatively simple arguments that show that these distances can also be considered for non-symmetric matrices and the properties tested. But it does make the presentation slightly easier to consider symmetric matrices. So for this talk, we'll assume that all our matrices are symmetric, just for ease of presentation. Okay, but I need to tell you what metric we consider to measure how far A is from being a PSD matrix. And so we'll consider metrics which are norms. In particular, if we have a norm, then the distance from A to the PSD cone is simply the distance from A to the nearest PSD matrix B, where here B greater than or equal to 0 means that B is a PSD matrix, under some norm quantity squared. And the squared here is just for convenience. It's not entirely necessary. It makes some equations easier. So we have some norm, and we need to instantiate it. And when we instantiate it by a given norm, we'll get a concrete problem. So in this work, we consider two natural norms over n by n matrices. The first one is the spectral norm, and the second one is the Frobenius norm. So when we instantiate this norm with the spectral norm, we get a concrete instantiation of this problem. And when we instantiate with the Frobenius norm, we get another instantiation. And the query complexity of these two problems will be different because they're two different distance metrics. So the spectral norm gap says the distance from A to the nearest PSD matrix B and spectral norm squared is at least epsilon n squared. And recall here that the squared spectral norm is just the square of the largest singular value of the matrix. If we instead use the Frobenius norm, we get the following definition, which is that the distance from A to the nearest PSD matrix B in Frobenius norm squared is at least epsilon n squared. And recall that the Frobenius norm is just the sum of squares of all the entries of the matrix A. So in particular, it's the squared Euclidean norm of this matrix just thought as a vector. So what that says is this Frobenius norm gap is actually the Euclidean distance from the matrix A to the PSD cone when you think of these as points in n squared dimensions. So this really is a distance in Euclidean space. Okay, so why are we considering this parameterization of epsilon n squared here? Well, it's easy to see that because we have bounded entries, the biggest that these spectral norm squared and Frobenius norm squared could be is both of them could be at most n squared. So the natural parameterization is to have this value epsilon, which is between 0 and 1. And we want our algorithms to depend only on epsilon, which is somehow the fraction of the overall mass of the matrix A, which is far from the PSD cone, which is contained in negative parts. And it's easy to see a standard fact that the spectral norm is always at most the Frobenius norm of the matrix. So that says that if we have an epsilon spectral norm gap, we also have an epsilon Frobenius norm gap. But the converse is not true. because the Frobenius norm distance to the PSD cone can be much larger than the spectral norm distance. So this in some sense says that the Frobenius norm gap is more general than the spectral norm gap. And we also have these very nice eigenvalue identities, which will be very useful for analysis. And what these eigenvalue identities say is that we can express the distance from A to the PSD cone under these two norms purely in terms of eigenvalues of the original matrix A, instead of these complicated, distance to the nearest matrix as PSD. So firstly, for the spectral norm gap, it says the following identity says that the distance from A to the nearest PSD matrix B in spectral norm squared is equal to the maximum in magnitude over all the negative eigenvalues quantity squared. So you look over all the negative eigenvalues and you look at the maximum in magnitude and then you square it. And that's the distance to the PSD cone in spectral norm squared. Similarly, it's a case that the distance from A to the nearest PSD matrix B in Frobenius norm squared is equal to the sum of squares of negative eigenvalues of A. And both of these identities, they can be proved very, relatively straightforward using variational theorems for eigenvalues. But they allow us to work with much simpler quantities, such as the eigenvalues of the original matrix, in some sense simpler, rather than a minimum to overall possible matrices in the PSD cone. And so a quick example is a random matrix. So random matrices seem to be very far from PSD, but they don't have any big negative eigenvalues. For example, a random sign matrix, its biggest negative eigenvalue is only root n. So that means that it only has order n distance in squared spectral norm from the PSD cone, whereas it's fairly easy to see that it's at least n squared far in Frobenius metric from the PSD cone. So epsilon for the spectral norm would be 1 over n, but epsilon for the Frobenius norm would be only a constant. So that we can see the Frobenius can be much further. So now I'm ready to tell you about the main results of this work. So we'll begin with the problem when we instantiate it with the spectral norm. So with the spectral gap problem, we show that there's a non-adaptive algorithm for testing with epsilon spectral gap, which makes tilde O 1 over epsilon queries to the entries of A. And here this tilde O is only hiding log 1 over epsilon factors, so we don't have any direct dependency on n. Additionally, we show that any algorithm with a lower bound needs to look at least 1 over epsilon queries of the entries of A. And this lower bound holds even for adaptive algorithms, which could look and choose what the next query to sample is, whereas all of our algorithms are not adaptive. They fix the queries in advance of seeing them. So in other words, we characterize the query complexity of testing with spectral norm gap up to log 1 over epsilon factors. So now we can move on to the Frobenius gap. So the Frobenius gap, we show that there's an algorithm for testing with Frobenius gap, which makes 1 over epsilon to the 4th queries to the entries of A up to log 1 over epsilon factors. So this query complexity is a little bit larger, but that's because the Frobenius gap problem is a more general problem. And in fact, we show that the Frobenius gap problem is a strictly harder problem by showing a complementary lower bound. We show that any non-adaptive algorithm for testing with the Frobenius gap needs to look at least 1 over epsilon squared queries to the entries of A. So this is a strictly larger lower bound than the upper bound for spectral norm gap, which shows that the Frobenius gap problem is in fact harder than the spectral gap problem. And this lower bound is very general, and it also immediately results in lower bounds for a number of other spectral problems. New lower bounds for testing the Shannon-1 norm, the Chi-Fan norms, and also something which is known as the residual K-tail of the matrix. So the picture is like this. For the spectral norm, we characterize the complexity of testing up to log 1 over epsilon factors, tight at roughly 1 over epsilon. However, for the Frobenius norm, the upper bound is tilde 1 over epsilon to the 4, whereas the lower bound is tilde omega 1 over epsilon squared. So there's a quadratic gap between the upper and lower bounds for the Frobenius norm, and this is an open problem to resolve this. Okay, so I want to talk briefly about the high-level ideas which go into the analysis of these algorithms. And remember, the algorithm is just going to sample random submatrices and test whether they're PSD. So all we need to show from an analytic perspective is that if we have a matrix which is far from PSD, one of these principal submatrices will not be PSD. And so the main takeaway I want to give you about the spectral gap algorithm is that we're going to be able to get away with analyzing tight bounds for the query complexity only by using classical scalar value concentration of random variables. In other words, we won't need any random matrix concentration, only scalar valued random variables. And remember, the spectral norm gap says that we have at least one negative eigenvalue, which squared value is larger than epsilon n squared. So the idea is that we know that there's some eigenvector, associated eigenvector x, such that if you look at the quadratic form of a with x, xax is less than negative root epsilon n, root epsilon because we have to take square roots here. So we know that there's some eigenvector which has a very large negative quadratic form. So here's what we're going to do. We're going to sample the submatrix with a random subset of indices, and we're going to hope that the quadratic form on this principal submatrix with the same eigenvector x projected onto the coordinates in the sampled subset T is still negative. If we can show that, then we can immediately deduce that AT is not PSD. And to do this, we're just going to need to analyze this scalar concentration of this random variable, which is this random quadratic form, over the choice of the random subset T. And at the end of the day, we never needed to actually know this vector x, because the algorithm itself is just going to test whether AT is PSD. So if we can prove in the analysis that any vector has a negative quadratic form with this principal submatrix, then we immediately conclude that it's not PSD, and we'll determine this when we compute its eigenvalues. So the picture looks like this. We have our big quadratic form with this this eigenvector x, which is very negative. It's less than negative root epsilon n. And so what we'll do is we'll project, we'll hope that because this quadratic form was so negative, that when we project onto a smaller subset of coordinates T, the quadratic form is still negative. In particular, this quadratic form with a smaller principal submatrix AT, with the same vector projected onto the coordinates in T, is still negative. And again, if we can show that this is the case, this will prove that AT is not PSD. So a first step, we're actually able to show that relatively straightforward manner that one principal submatrix, a T by T principal submatrix, where T is at least 1 over epsilon, suffices to find a non-PSD submatrix. And the proof of this is relatively straightforward. What we're going to do is we're just going to consider this quadratic form, and we'll just compute its expectation and its variance. And then we'll show from the variance computation that if T, the number of indices we sample, is at least 1 over epsilon, and that's good enough to apply Chebyshev's inequality to show that the quadratic form will be negative with good probability. So that's great, because this actually already gives us an algorithm just by doing the variance computation. It gives a 1 over epsilon squared query algorithm for this problem. On the other hand, we wanted something tighter. We wanted a tilde O 1 over epsilon query algorithm. So we're going to need to go a little further than just this argument. So the first question is whether this variance computation was tight, whether we actually, it was loose and we could do better with just one principal submatrix by a different analysis. And the answer to that question is unfortunately not. And the reason is because we can hide a very small fraction. We can hide the so-called negative mass, which is something you can define, of the matrix A into a very small fraction of the rows and columns. So here there's a small subset S, which holds all these negative ones. And so to even test whether this matrix is PSD or not, if I randomly hid these rows, I would need to look at least 1 over epsilon entries of this matrix, because it's only an epsilon fraction of the matrix. So in particular, if I had a 1 K by K matrix, K better be at least 1 over epsilon, otherwise I'm not going to even see this subset. But a solution to this is that because we decided to concentrate all the negative mass in a very small subset of rows and columns, the mass is very concentrated. So we only need to see like a very small submatrix which intersects this negative rows and columns for it to not be PSD. In particular, a 5 by 5 submatrix would not be PSD if it intersected one of these rows. So our solution is to query many smaller submatrices and hope that one of them intersects the bad set of negative rows. So at a high level, the algorithm is as follows. We're going to sample these submatrices at log 1 over epsilon different scales of sizes of the submatrix. So we'll sample 1 over epsilon matrices of 5 by 5 size, 1 over root epsilon matrices with 1 over root epsilon by 1 over epsilon to the 1/4 by 1 over epsilon to the 1/4. And then at the end, we'll just sample one matrix of size 1 over root epsilon by 1 over root epsilon. And at every single level, and all the levels in between with power raised to 2, the total, we set it up so the total query complexity is only 1 over epsilon. And we just need to show that at least one of the levels will find a non-PSD submatrix. And the main result that we show is a classification theorem. There's a lot of steps here that I'll need to skip, but sort of the key idea is that we show that either we're in one of these cases where A has this negative mass hidden in a very small fraction of rows, Or we can prove the variance is much smaller if that's not the case. Small enough that a single 1 over root epsilon by 1 over root epsilon submatrix will be enough to find a non-PSD submatrix. So in some sense, we classify all the ways the matrix could fail to be PSD. So that's all I wanted to say about the spectral norm gap. I want to say something very briefly about the Frobenius norm gap. And recall the Frobenius norm gap says that the sum of squares of negative eigenvalues of A is at least epsilon n squared. So I'm going to use this funny notation here, A NSD, to denote the sum of squares of negative eigenvalues of A. Now, the difficulty with the Frobenius gap is that this negative part, this NSD part, can be spread out over many light negative eigenvalues of A. So there's not going to be any large individual eigenvalues that will concentrate when we look at this in a single direction. So we need a different approach than the approach for the spectral norm gap. In particular, we're going to need tools from random matrix theory to show concentration. But the issue is that even with these tools, it's not going to be possible to handle this NSD part directly. And the reason is that concentration is only going to be possible for things that are large. We're only going to be able to preserve the large top singular values and eigenvalues when we go down to a smaller submatrix. So our solution is at a high level is we're going to look for a proxy for this NSD part, which only depends on large singular values. In particular, we'll show one of the two things, this so-called k-head, which is the sum of the top k squared singular values, or the Schatten-1 norm, which is the sum of all the singular values. It's easy to see that we'll be able to show that if A is PSD with bounded entries, these quantities have to be small in a certain sense. So what we'll be able to prove is a certain dichotomy theorem. We'll be able to prove that either we can show that this k-head, the sum of squares of top k singular values, is too large for the matrix to be PSD, or if we can't do that, we'll prove that we can show that the Schatten-1 norm of the sampled submatrix is too large, both of which we'll do in 1 over epsilon to the 4th queries. And there's a number of tools that we'll need, but I won't be able to discuss them here, so you can refer to the paper for details on that. Okay, and I'll end with just a couple details about the lower bound. And the lower bound, it doesn't quite match for this Frobenius norm gap, but it is a lower bound of 1 over epsilon squared, which separates the complexity from the special gap testing problem. And the idea is that we're going to construct two explicit matrices, G1 and G2, which are going to have different spectral properties, any kind of different spectral properties that we want. For instance, G1 will be PSD and G2 will not. And they'll have this very special local indistinguishability property. At a high level, what this indistinguishability property says is that if I look at any small set of queries here to G1, and I see, like, for example, 0, 1, 0, 1 here, there exists a unique permutation of the rows and columns, the indices, such that if I permuted them and looked at the permuted samples in G2 instead of G1, I would have actually seen the same exact observations. So what this indistinguishability property says is that if I either get to look at a random query on a permutation of G1, or I see a random permutation of G2, the distribution of what I actually see is actually entirely equivalent. It's identical. So there's no variational distance between these two distributions of observations. And there's several details involved in this construction, but at the key is just some very simple idea based on cycle graphs. And in one case, G1 will actually be the adjacency matrix of two cycle graphs, two disjoint cycle graphs, and G2 will be one cycle graph. And we'll show that these satisfy, after an amplification step, the desired properties of indistinguishability. And the actual construction plants randomly either G1 or G2 in several communities along the diagonal of the overall matrix. And the reason you do this is that if you have a non-adaptive algorithm and it samples a bunch of entries, only a very small fraction of these entries will be able to land in one of these important communities, one of these planted graphs. And because each of these planted instances is robust to a small fraction of queries, we won't be able to tell the difference between it being PSD or not. We won't be able to tell the difference between the two cases at all. And this will also yield lower bounds for the other problems that we mentioned. And so I'll end with some open problems after having to discuss at a high level this lower bound. So the biggest open problem is to close this Frobenius gap problem. We have an upper bound of 1 over epsilon to the 4th, but the lower bound is only 1 over epsilon squared. And there seems to be very key barriers to improving the upper bound. So there's some conjecture that the upper bound is not tight, but we'd have to overcome some barriers. And finally, a very interesting question is to give any non-trivial upper bound for estimating the Schatten-1 norm in the bounded entry model. So far, there's actually several lower bounds, including the lower bound from this work for the Schatten-1 norm testing. But to date, there's no known non-trivial upper bounds. So that's a very interesting open problem to resolve. So that was the talk. Thank you so much for your time.